Welcome to YMT215 Logic Circuits. We are still discussing Chapter 2, Number Systems, Operations and Codes. This is the fourth and last part. And in this part, we will speak about digital codes, error codes. We will not cover all possible digital codes. There are so many of them. However, we will try to focus on the most familiar ones, or the ones actually we need in some applications. Gray code, what makes gray code special is it is unweighted and not arithmetic. Arithmetic is easy. That means we can't apply addition, subtraction, division, whatever to it. It's not arithmetic. What does it mean, unweighted? Unweighted, that means we can't convert it to decimal or any other system based on the weights of the digits. So the digits of this kind of code do not have the proper weight. Weight means what? 2 to 0, 2 to power 0, 2 to 1, 2 to 3, and so on. No, in gray code, this doesn't apply. Why do we need to have such a code? We have some applications in digital systems, and specifically in coding, and sometimes in even transmission, data transmission, sometimes, I say in some cases, but in coding, especially for some encoders like shaft encoder, we have application where the change of bits should be minimum, adjacent bits. So adjacent numbers, not bits. Adjacent numbers means what? If I am having a chain of numbers 1, 2, 3, 4, so between 1 and 2, I should lower the change of bits, and that is not applicable in binary. How do I know? Let's just move a little bit to this table and I explain here. Look at this. We have decimal 0, which is in binary 0. Actually, let's represent it by 4 bits, okay? So we have a 4-bit block, and we have the gray also 4-bit block. Now for decimal, it will be same 0 for all systems. How about 1? Now for decimal, it's 1, and for binary 0, 0, 0, 1. Now, as I said, because we are just representing it by a block of 4-bit, okay? Gray code is the same. Now, 0, 0, 0, 1. So what are we trying to say, or what are we trying to give? Now look at this, the change of the bits. Now look at this. 0 is still 0. We are speaking about 0 and 1. They are adjacent, next to each other, okay? Here we have 0 not changed, 0, 0 not changed also, 0 not changed also, so we have 0 here changed to 1. Okay, the change is minimum, only 1 bit has been changed. For the gray code, it is also the same, only 1 bit is changed. Good. What's the point? Let's go to 1 and 2. So we have new adjacent 1 and 2. How about this? Let's have a look. Now 0 will remain same, 0 will remain same, but 0 will change to 1. 2 in decimal is converted to binary to 0, 0, 1, 0, or 1, 0 directly, because we have these 2 zeros at the beginning. They don't change much of the value. 1, 0. Now look at this bit. This one changed from 0 to 1. Look at this bit, from 1 to 0. We have 2 bits changed. And this is not recommended to some of the applications like the shaft encoder. Okay, what is the shaft encoder? This will be actually your duty. I'll just give an idea about it later on, a little bit, while explaining about your assignment. And it will be your assignment. You will need to make a research about it. I'll upload the guideline of the assignment, the first assignment, to the website, to the distance education, and you'll see all the details. Now look at this. So we said we have 2 bits change. This 0 is changed to 1. This 1 is changed to 0. Okay, how about gray? Now look, 0 is still same. 0 is still same. Okay, fine. This is not changed. They have not changed in both cases. But how about this? 0 is changed to 1. 1 remains same. So we have only 1 bit change in this case, and that is the advantage of gray. If you check all these codes, it applies. Now look at this, 3 and 4. For 3 and 4 in binary, 0 remains same, but here 0 changes to 1, 1 bit change. 1 changes to 0, 2 bits. 1 changes to 0, 3 bits. So we have change of these 3 bits. And that is not good. for such applications like the shaft register. It is very susceptible to the change of bits. And in this case, look at the gray. 0 holds the same value, 0 changes to 1, 1 remains same, 0 remains same. We have only change of 1 bit here. Okay, good. So now we know what gray code is. We know that its main characteristic is it changes only 1 bit with the adjacent numbers. Adjacent means we move from 0 to 1. These are adjacent. 1 to 2 also adjacent. Okay, and so on. And this is a great feature that applies to many requirements of different digital devices, like one of them, as I said. This is just one. There are so many others. Let's move on and see how can I convert a binary code to a gray code. This is extremely easy. You have a binary code, start from the leftmost or the most significant bit, the MSB. Take the MSB of the binary code, and it will be your first number from right to left. Okay, from left to right of your gray code. So what does it mean? We have a number here. Let me show you. We have a number here. This is the MSB of the binary. So this is the number. And in order for us to convert it to gray, the MSB of the binary will be the first number from left to right here. Left to right. Okay. So we are starting from left to right. All right. No change. The MSB of the binary is the first number of the gray. I wouldn't say MSB of the gray because we don't have weights for gray codes. All right. How about the next one? We start from right, from left to right. Okay. The next code of the gray, or the next bit, not code, the next bit of the gray code is generated by summing up these adjacent numbers. 1 plus 0, what's the value? Is 1. Place it the way it is. Now, if there are carries, ignore them. This is the point. Add the adjacent pair of binary codes here. These are the adjacent. This one and this one. These two are adjacent. Okay, so we sum up these two. If there is any carry, ignore it. Discard it. Now, 1 plus 0 is 1. Actually, there is no carry. There is no problem. How about the next? This one with this one. These are adjacent. The next adjacent. 0 plus 1, again 1, with no carry. How about 1 plus 1? The next bit. 1 plus 1 is 0. Remember, 1 plus 1 is 0 with 1 carried. So we have 1 carried here. Ignore it. Cancel it. We don't have a need for any carry. 1 plus 0 is 1, and that's the gray code. That's it. So 1 0 1 1 0 is represented by 1 1 1 0 1 in gray. All right. How about the other way around? If we have a gray code and we want to convert it back to binary, what can we do? It's also straightforward. It's easy. You take the leftmost bit. I wouldn't say MSB because this is not weighted. Again, unweighted. Take the leftmost bit, drop it down the way it is. This is the MSB of your binary. This is MSB. I can call this one MSB. Then we don't add the adjacent. No, we add diagonally. So this is a diagonal. 1 plus 1. We go in a diagonal way. The one we created for the binary plus the next bit from the gray. Next bit means what? This one, we are done with it, move to the next. 1 plus 1, the result is 0. With 1 carried, discard the carry. So we have 1 carried here, ignore it, remove it. Alright, so the result is 0. How about the next bit? Go in a diagonal way, we are done with this one. 0 plus 0, that's 0, we don't have carry. 0 plus 1, that is 1. We don't have carry also. 1 plus 1 is 0. With 1 carry, discard the carry, and you got your binary code back again. I hope this is clear. Let's take another example so that the idea maybe will be a bit closer to your mind or understanding. If we have a binary code, we want to convert it. For binary code, add the adjacents. First, we start by the MSB. This is the MSB. Drop it down, and it is the leftmost bit of the gray. there is no change. Then add the adjacent 1 plus 1 is 0. 1 carried, ignore it. We don't have anything about to do with the carry. 1 plus 1 is 0 directly. 1 plus 0 is 1. 0 plus 0 is 0. 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 1 is 0 with 1 carried, ignore the carry, 0. 1 plus 0 is 1. That's it. This is your gray here. If we want to convert this one back again, it's easy. Take the diagonal. This is the same. Then add the diagonal. 1 plus 0, that's 1. Then 1 plus 1, that's 0, and so on. You will get back the same code here. All right, let's apply the other way. We have a gray code. We want to convert it to binary. All right, now look at this gray code. We listed down now 1 0 1 0 1 1 1 1. The first here, the leftmost bit will be the MSB of our binary. Drop it down the way it is. Then take this number, sum it up with the next digit. 1 plus 0 is 1. 1 plus 1 is 0 with 1 carried. Ignore the carry, I wouldn't even say. So directly I would say 1 plus 1 is 0. 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 1 is 0. 0 plus 1 is 1. 1 plus 1 is 0 again. So this is your binary code. All right. So I said about the assignment. One of the most important applications of gray code actually is the shaft encoder. And what I want from you is to do a quick research about the shaft encoders and explain how they work, for what they work, and few applications in reality or real systems. I want you to write it in a nice academic way and present it in a Word file, send it to, through the online education system. I'll, of course, create a submission environment for you to add your assignments, and I will also determine the deadline for submission. All right. Now, gray code is one of the codes that we use in digital systems. We have other codes. What kind of codes do we have? One of the very frequently used, we use it every day in our life while dealing with machines, is the alphanumeric codes, or the codes that actually help us change whatever we have as alphabet or alphabetical representations to digital codes. Now we have a keyboard, and this keyboard is full of symbols, numbers, letters, and so on. How do we represent them in computing way? The computer doesn't understand ABC, for example, or maybe hash code or exclamation mark and question mark. How do we represent them? We have to exchange these codes and create series of ones and zeros. We have to convert them to binary. In order for us to do this, we need to have a code or a representation or an exchange between the alphabet or alphanumeric and binary. And this is what we have actually in our reality. We have what we call American Standard Code for Information Interchange. We usually write it this way, ASCII, and pronounce it ASCII. ASCII, the way we write it this way, ASCII. Okay, this ASCII is a very popular code that changes or converts each and every key and letter you see on your keyboard to a digit or a digital code or a digital representation. How many bits do we have for the ASCII? The ASCII started by 7, so we have actually 2 to 7. If we say 7 bits, then how many combinations do we have? 2 to 7, right? So 2 to 7 is equal to 128. Okay? And that accommodates for 128 characters. All right, 128 characters, good enough. Why? Well, if you say we are dealing with English, 26 plus 26, well, we have more than 26 plus 26. But the idea is like we have small letters and capital letters or lowercase letters and uppercase letters. We also have symbols, special characters, some you can say escape characters and so on. That's why we have to accommodate for that. It's not just the letters that we have also other symbols. So 128 will do for English representation. We can accommodate for all symbols and special characters. Now for the ASCII, in reality, it is not exactly 7. It's actually 8. 8-bit code. But the MSB of this code usually is 0. It is left empty, the MSB. Ultimately, we end up by 7, actually, 128 characters. So we go from, if you think about it in hexadecimal, we go from 00 to 7F. 7F means what? 7 is represented by 0111, sorry, 0111, 3 ones. Then F is represented by 4 ones. Again, 0111, then 1111. And that's why we said 0 at the beginning. The MSB is empty, left empty, or 0. In this case, we don't have any code for it based on the system. All right, so we accommodate for all the symbols and special characters or whatever. Now, one thing I would like to say is the first 32 ASCII characters or codes are left for non-printable codes for null. Null is not printable actually. We cannot display it, but we have to code it. Line feed also is not printable. Escape is also not printable, but we have to represent it. Start of text, and so whatever similar to it. Similar codes that are not printable in our system. All right. How about the other representation of systems? We have the letters. The letters we have in our alphabet. I speak about English. We have the lowercase and uppercase. We have 10 digits from 0 to 9. Also, we have punctuations. We have special characters. We have symbols, and so on. But we'll accommodate. 128 will do for English language. How about other than English language? How can we accommodate? Well, IBM invented a solution for that. We'll speak about it in a while. Now look, all these I said earlier, because I don't memorize all of them, and you don't have to, unless you have a need for knowing all these. I mean, you don't have to memorize the codes. That's not, I mean, unless you have a specific application to know, for example, what is this in binary, you don't have to memorize any of those. But those, the first 32 from 0 to 31 in decimal, they are control characters. Not printable actually, we don't print them to the screen. Next to that, we have space, we have exclamation mark, quotations, double quotations, and so on. Then we have the digits, then we have, after that, some symbols. Then we start with the uppercase. Uppercase are smaller in binary than lowercase. I think you are familiar with that. Okay. Try to remember this. This is important. A is represented by 65 in decimal, okay, which is 1000001 in binary, okay, or hexa is easy, 41, right? And lowercase a, this is uppercase of course, is represented by 97 in decimal or 61 in hexa. Now these are important. You can think of them, I mean, as a key, or they are key actually for other or the rest of alphabetical letters. All right, we have also for delete, for other braces, bar, or whatever. All right, let's not just extend the talk about ASCII. This is the standard ASCII, right? How about extended ASCII? As I said earlier, how about other languages other than English? Those that we have some languages with special letters not included in the English alphabet. Well, for this case, IBM discovered a way, and they refer to it by extended ASCII. The extended ASCII is exactly accommodates for all these by considering the left MSB. We said we leave the MSB, it was left here. Instead of FF, we said 7F. In this case, we don't have 7 here, we will use 8. And that will take us to 256 characters. Well, languages similar to English language, like Latin alphabet, Greek letters, some mathematical symbols, some drawing characters, bar graphing characters, shading characters, all these would be accommodated for, but up to 256. How about other languages that we know in our life? How about the Mandarin, the Chinese, that has so many letters, and its representation is not easy, it's not English-like. How about Arabic? It's also difficult, the representation of letters, although there are not so many letters, but the representation of the letter itself is not easy. Plus we have a movement for the letter. So some, a letter on top of a letter, small letter. Also, if you think about other Asian languages and so on. So they said, well, instead of having the extended ASCII, how about we go for something, we call it the Unicode. We use universal character set, some universal set for the character, USC, and we represent all these special languages by some way. So 256 combinations will not be enough. We will increment the bits. Increment up to what? Well, we can go 2 to the power 16. Is it enough? No, not enough. So they decided to go for even further. We have up to 2 to power 6, not 16, 32. That goes more than 100,000 even. So we may go like up to millions or so. Well, millions, I don't think we need such combination. Usually we can go like 100,000, 150, 140,000 different characters for all languages on Earth. Most likely. Of course, I can't guarantee such a thing because we don't know all the languages and they have not been all coded to our computerized machines. But that's good enough for the languages, the popular languages that we know, and that's how we accommodate for them in our computing system. All right. Let's leave all the codes and go for error detection. Error detection means what? Now, when we speak about digital systems, we spoke about the benefits at the beginning. The first chapter we said digital systems or binary systems are widely used because they are not susceptible to errors as much as the analog systems. Well, okay, we understood that part. Why? Well, we have 0, 1 only. If we have an error, it will be either a 0 is changing to 1 or a 1 is changing to 0. Good enough. How about the detection method? How do we detect if there is any error in the transmission? What does it mean, transmission? Now, imagine you have a pen drive and you want to place some data to your computer. There is a transmission from your pen drive to the memory of your computer, or vice versa, from your computer to the pen drive. Or if you are sending an email to some of your friends, let's say in USA or anywhere in the world, the letters you type or whatever within the message, special characters, dots, whatever, even if you send like some emotions in your own text, they will be converted to digits, binary digits, series of ones and zeros, and they will be sent through a transmission line. Okay, so this is what we call transmission. We have a sender and a receiver. And between the sender and the receiver, while these bits are moving, there may be an error. Again, the error is a change of 1 to 0 or 0 to 1. Why? Because simply we don't have any other. We have only 0 and 1 in our binary system, and that is why it is simple and easy to detect its error and to deal with. Well, how do we detect? We have different ways for error detection. The simplest one is the parity method. This is not parity, it's parity, okay? Because usually we get stuck with this parity. Parity, it's pronounced parity, and it is based on the change of the total number of bits of ones to be even or odd. What does it mean? Now, assume that you have a binary code, and this binary code has certain number of ones. The number of ones will be one of two things, either even or odd. If it is even, then the number of ones will be either 0 or 2 or 4, 6, and so on. If it is odd, then it will be 1, 3, 5, and so on. So we count the number of ones. If it is even, then we call the number of ones in any combination is even. If it is odd, then we call it odd. How about the parity? Now, if we know that the number of ones is even, is like 4 or 8 or whatever, then we can create what we call even parity or odd parity. If you're going to send using even parity, make all the number of ones inside your code even. If it is not even, add 1 to it. What does it mean? Now, let me just give you a simple example. Let's say 1, 0, I'm sorry about this typing, 0, 1, okay. Let's say this is a code. How many ones do we have? 1, here we don't have, here we don't have, here is 1. All right. So we have 2 ones, that's even. Now let's say we are discussing even parity. Even parity, we have even parity and odd parity. We will reserve a bit here for the parity. We refer to it by P, okay? Now since we have 2 ones, we keep this one 0. Why 0? Now count all the ones inside this bit, inside this code. We don't have here 1, we don't have here, we don't have here, then this is 1. So we have 2 ones, that is even. We send this code. When we receive it at the receiver side, we know that it must have an even number of ones. So it will count them. How to count them? Well, count the ones. If they are not even, then we have an error. Let's say this one is changed from 0 to 1. Now count the ones. We don't have 1, we don't have 2, 3. It is not even. Then it will tell you there is an error in your code. Also, we have the odd parity. The odd parity, it counts the number of ones. If it is odd, then it places 0 here. If it is even, it places 1 here. So let me give you a few examples, okay? Just directly so that you understand. Now this is even parity. Look at this. This is BCD. If we are sending a BCD, now 0 is represented by 4 zeros, right? Remember, the BCD is transferred. Any number from 0, any digit from 0 to 9 is converted to 4 binary digits. Okay, how about the even parity? 0, 0, 0, 0, that's even number of ones because we don't have 0 is even. So you place the parity bit by 0. How about 1? 0, 0, 0, 1. We have 1 here. We must change the whole number of ones to 2. So we add 1 to it. How about odd parity? Now look, 0, 0, 0, 0. We have even number of ones. We have to change it to odd. We place 1 here. All right. So again, if you couldn't catch the idea, I'll just give you 2 examples, 2 different examples randomly. I'll just select randomly. Let's take, this is 6, okay, not 6 actually, this is 4, I'm sorry. Let's take 6. Right, look at 6, 0, so we have 1 and 1, 2 ones, that's even. We don't add any even parity, it remains 0. So we must not add any 1 here. If you check the odd parity, it will be exactly the opposite. Why? We must change the total number of ones here to odd. Odd means what? We have 2 ones, we must change it to 3. We add 1. And this is separate. It's for the parity check, for the error detection. Apply to any. Now here we have odd, we add 1 to convert it. Here we have odd, we don't add 1. It's what we need. Here odd, we don't add anything. Here even, we add 1, and so on. I hope it's clear. Now, For error detection, we check the parity bit will determine based on your sequence. If there is any change in the sequence, most likely we will have a change in one bit, most likely I say, because in some cases more than one bit will be there. More than one bit is really hard for parity check. Actually, odd number of bits is possible, but it's not likely, it's a very rare case. And in that case, we will check if the even parity is sent, then we expect even number of ones. If the odd parity is sent, then we expect odd number of ones. Okay, let's take an example. Now let's say we have this BCD sent 0, 1, 0, 1, and if we are considering even parity, how many ones? Count them. 1, 2, that's even. So for even parity, you add 0. Why? Because they are already even. You know, if you add 1, it would be actually you will create an error. Why? We will have 1, 2, 3 ones, and that will be invalid. So you add just 0, and in that case, you have your parity check bit, even parity, and you have your own code to be sent. Let's say for some reason, one bit changed. This one changed from 1 to 0. It's possible during the transmission. How do we know it is wrong or there is an error in the code? First of all, at the receiver, we know that we are using the even parity. It is agreed upon. It's like a code between the sender and the receiver. So we know that we are using even parity. And we count the number of zeros. The number of ones. Here we have only 1, 1. And in that case, we have an error. Can we detect which one has an error? This is a bit higher than our application now. That has like special applications in digital communication, and we will not speak about it in this course. So it's enough for you to detect there is an error. The detection of an error you request, and it is actually done automatically. You don't request it as a human being, the computer does it. It says that there is an error in this message, resend it. And that's how it is done. All right, let's take an example if it's not clear. Add an odd parity system receiver, an odd parity receiver, system receiver receives the following code groups. So we speak about a receiver. Why? Because we speak about a system that receives. And an odd parity. Odd parity, we expect an odd number of ones. So the question is telling, determine which groups, if any, are in error. Okay, we need to count. 1, 2, 3. This is fine. 1, why? Because odd. 1, 2, 3. Also fine. 1, 2, 3, 4. Error. 1, 2, 3, 4, 5, 6, 7. Fine. 1, 2, 3, 4, 5, 6. Error. That's it. If we go other way around, not odd parity, even parity, this one will be error, error, this one will be fine, this one will be error, this one will be fine. And I hope you understand the idea. The last part, we have the cyclic redundancy. Now for the parity check, as I said, it's valid only for one bit, usually odd number of bits, which is a rare case and not that much efficient. For the cyclic redundancies, usually the method followed in our computers nowadays. And it's not just for transmission over the network, as I said earlier, it is used for memory like CD, DVD, hard drive, pen drive, and so on. Right. What is the cyclic redundancy? Cyclic redundancy is applied based on long division. And a method we check the sum with if we have a zero remainder or not. If we have a zero remainder, then our code has no error. Otherwise, we have an error. So what is this checksum or long division we are speaking about, and how can we create it? This is extremely simple. You don't have to worry much. You don't have to think about the mathematical representation much. expect something like this. We have a code, and this code is represented by a polynomial. Polynomial means what? You know from mathematics what polynomial is, but for this polynomial, we keep the coefficients of the polynomial restricted only to 1 and 0. 1 and 0 means what? Either we don't have x, it's cancelled, whatever the power is, or we have it. Okay? Then we apply long division. And luckily, in order for us to avoid any problem with the long division, we have a method to shorten the long division, in this case, by applying what we call Modulo-2, or the XOR operation. And now, I haven't explained about the XOR operation. Actually, I'm trying to synchronize the topics. For some reason, maybe some of you even think, those who are studying discrete mathematics, they say, oh, why our instructor didn't upload anything related to discrete mathematics after the first chapter. I'm trying to synchronize the topics between programming languages, logic circuits, and discrete mathematics. Now, discrete mathematics, I'll catch it the coming week. I'll give you 1 or 2 chapters, but I wanted you to understand these topics that I'm explaining about now, so that we go in a much easier way in the other topics of discrete mathematics. And let's just limit the talk about discrete mathematics up to this, because next week I'll upload 2 chapters, don't worry. All right, so here we have the Modulo-2. Modulo-2 means what? Actually, you studied this in last year in algorithm and programming. It's the modulus operation, the remainder of the division based on 2, base 2. So we take the Modulo-2, or luckily, actually, there is an easier way, because it is based on subtraction or addition and shift. Why? Because we ignore carries here, we discard the carries. We can apply it directly to 2 bits, like 1 and 1, for example, here in this case. We can apply it by XOR operation. Now, I didn't explain about XOR. Now I'll explain about it. Now have a look. Let's say we have 2 bits, 0 and 0. If we apply the XOR operation is represented by something like this. A plus, a circle inside of it plus. So 0 XOR 0. The outcome or the result or the output is 0. 1 XOR 1, the output or the outcome is 0. 0 XOR 1 is 1. 1 XOR 0 is 1. An easy way to remember them: when the bits are same, the inputs, the outcome is 0, or the output is 0. 0, 0, 0. When the bits are same, the outcome is 0. When the bits are different, 0 XOR 1 or 1 XOR 0, then the output is 1. It's easy. This is easy. If 0 XOR 0 or 1 XOR 1, the bits are same, 1 and 1 are same, 0 and 0 are same, then the output is 0, otherwise it is 1. That's how we apply it. What is the procedure? How do we apply the whole concept for sending data on a transmission line or whatever, and how do we check if our data is in error or not? Now, this is not difficult. What we need to do is like this. We take our code, whatever the code, that means whatever binary number to be sent. Now, we don't usually send a binary number, a binary code. I'm sorry about saying number. A binary code to be sent. We take it, we add to it a fixed size generator or a key generator. Okay? It's fixed. Now, you choose the size. Usually, in logic circuits applications, we choose not a very long generator. It depends on the application, but often it is shorter than the data. So let's say your data 10 digits, maybe you can use a generator or key generator in this case, key generator of 4 bits maybe, okay, 5-bit length. Then we have to add a number of zeros equal to the generator code, to the data to be sent. Okay, we have some data. It doesn't matter how many digits, but what we need to know is the generator code, how many digits. Let's say 4 digits, you need to add 4 zeros to your data from right side. You append from the least significant bit and onward. All right, then what you need to do? You need to divide your data with the appended zeros by the generator. Divide, this is a long division, and in order for us to achieve it, instead of going to the long division, we can take the XOR operation, bit by bit, 2 bits at a time. Once we are done with the modulo operation, we see if the remainder is 0, then we send the data the way it is. If the remainder is not 0, then we have to replace the zeros that we appended to our data by the remainder. So we take the remainder of this division, we add it to the data if it is not 0. If it is 0, you don't have to change because there are already zeros that you appended. All right. At the receiver side, we do the exact same process, but in opposite. We apply, again, the long division by the generator. We must know this generator code. Both receiver, sender and receiver must know the generator code. And we apply the same process. We need to apply the long division of the received code by the generator. If we get 0 as a remainder, then our code is correct, the received code or message. If there is a remainder, then we have an error. And then we have to ask or request the retransmission of the same message. All right, this is the schematic diagram of how it is done. Usually I don't ask these as questions in the exam, but it's for you to know. You can consider the data bits or in the message as Y. We need to append the generator or equal to the generator length of zeros to it from this side, from the right side. Okay. Then we take the Modulo-2 of the bits with the generator. If there is a remainder, okay, now if there is a remainder, we append it to the data and we send. If there is no remainder, then send as it is. And that is how it is sent. My data with appended zeros to it, or my data with appended remainder to it. Then at the receiver, we have the sent data. We need to apply again the division or the Modulo-2 subtractions. Here addition, but it's somehow a subtraction XOR operation. And we check the remainder. If the remainder is 0, then that's it. We don't have any error. We got our data right. Otherwise, we have a remainder and we need to ask the retransmission of the data. Maybe it's a bit difficult for you to visualize it now. Let's take an example, and with this example I hope things will be clear. Now look at the example. Determine the transmitted CRC for the following byte of data. Byte, 8 bits. We refer to this data as a message D, and the generator, this is given to you also. Data message is given, and the generator is also given. Now look at the message, it's byte, and the generator is 4-bit. Now it doesn't matter, it may be 3, it may be 5, it may be 8, 1 byte. So do not be surprised if I change this one in length when I ask you questions about it. Okay? Now what we need to do is we need to create the CRC code to be sent using this generator. So in order for us to do that, we have to apply the long division or the Modulo-2 for this operation between the data and the generator. Before that, we need to append a number of zeros equal to the generator. So our data is 110100011. We need to add 4 zeros, 0, 0, 0, 0. Why? This is the length of the generator. So your data after change would be, let's say, D prime or D dash. And in that case, we will have a new version of this sequence. We need to apply the long division now. with the generator. The long division is done in an easy way by XORing these bits from left to right, one at a time. So we XOR one with one. So line up this, our generator. This is our generator. Line it up with your data, same. But do not forget to append these zeros to the data. This is appended, and we have our generator. Line it up with the same from the left side, leftmost. Now apply the XOR. 1 XOR 1, we said when they are same, it's a 0. So here 0, you don't have to type it. 1 XOR 0 is 1. 0 XOR 1 is 1. 1 XOR 0 is 1. Drop 1 0. Drop one of these, not 1 0. Drop one of these digits, which is a 0. All right, apply the same. Again, take this one back again, line it up with the remainder here, and apply the same process. 1 XOR 1 is 0. Don't type it. 1 XOR 0 is 1. 1 XOR 1 is 0. 0 XOR 0 is 0. Drop the next digit, 0. Drag this one again and apply the same XOR. 1 XOR 1 is 0. 0 XOR 0 is 0. They are similar. They are same. When the bits are same, zeros, ignore them. Then 0 XOR 1 is 1, 0 XOR 0 is 0. Now drop 2 digits. Why? We lost 2 digits here. Drop 2 digits at the same time. Alright, 0, 1, 1, 1. Why 1, 1? These two will be dropped as the arrow indicates. Apply the same process. 1 XOR 1 is 0, 0 XOR 0 is 0. 1 XOR 1 is 0. 1 XOR 1 is 1. Then we need to drop 3 digits. These 3 at the same time. Why 3? We lost 3 digits here, so we need to accommodate for them. Okay. 1 0 0 0. XOR it with the same generator. 1 XOR 1 is 0. 0 XOR 0 is 0. 0 XOR 1 is 1. 0 XOR 0 is 0. Drop the last digit. This is a remainder. Now we cannot apply XOR. Why? 3 digit less than 4 digit. Here we have 4 digits. So this is a 3-digit code. It's smaller than this, so it's a remainder. There is no modulo here. In this case, it's a remainder by itself. All right. So in this case, what will we do? We will append 0 here, okay? And then we will add it instead of these zeros. My data will not be only with zeros appended to it. No, this one. It will be 0, 1, 0, 0. Sorry about this bad typing, okay? So this will be our data. Now look, so we appended it. If you apply again the long division after appending the remainder, you must get 0. So this is my data after the change, the prime, after appending the remainder. If you apply the long division with the generator, with this message after appending the correct remainder in this case, you must get 0. You must. If you do the same process, ultimately you will get 0. And you try it, the same process. 1 XOR 1 is 0, 1 XOR 0 is 1, 0 XOR 1 is 1, 1 XOR 0 is 1, drop 1. And you keep on moving, XOR again, XOR again, XOR again. If you get zeros, then your process is correct. So you can send this data. All right, this is your CRC data. I asked similar question once in one of my semesters, one of the previous semesters. It was just a straightforward, even shorter than this, but most of the answers were wrong. I don't know why. Pay attention to this application. All right, let's take this example. Let's say this is my code, and for some reason, the one here, now look, 1, 1, the rest of the code, this one is changed to 0. An error in the transmission. So in this case, how can we solve it? How can we know that there is an error? At the receiver, what we need to do is we need to apply the long division again. This is what we did. If you apply the long division and you get 0, 0, then your code is fine. Otherwise, there is an error. We willingly changed this one, the 0 to 1. If we apply the long division, we will have a remainder for sure. Apply the long division. You can go through the same process. I don't want to go through it. It will take our time, but it's easy. I'll just repeat what I said earlier. 1 XOR 1, 0. 0 XOR 0, 0. Y, same bits. 1, 1, 0, 0. That's 0. Then 0 XOR 1 is 1. 1 XOR 1, sorry, 1 XOR 0 is 1. Drop 2 digits. XOR again with the generator. And do the same process. If you get zeros, then your message is correct. However, we changed this one willingly to see if it works or not. We get a remainder. That means there is an error. We must not get a remainder. We must get zeros. And in that case, if there is an error, it will be indicated that we have an error, and you should repeat sending or resend the message to the receiver. That's it for this chapter. And we are done with chapter 2. It was long, yes, but all the topics are actually needed, and they are a base or foundation for what will come next. I will try to start chapter 3 very soon. However, I will just focus on discrete mathematics this week, the coming week, a bit more than logic circuits. But I will settle at least one chapter of logic circuits. I'll upload also your assignment, and until our next session, have a good time. Goodbye.